Today we are going to learn about electromagnetic force. Let us start with the basics. We all have seen the magnet in the childhood and most of us has played with the magnets. These magnets attracts other magnet or metallic objects like iron. Magnet has two poles, North Pole and South Pole. North Pole repels North Pole. South Pole repels South Pole. Only opposite poles attract each other. We all have learned and felt this force of attraction and force of repel while playing with the magnets. All the magnets has two poles. If you break the magnet into small pieces, still all the pieces will have two poles, that is North Pole and South Pole. Magnet generates the field around it. If something is put into this field, it could be affected by this magnetic field and object would experience by some force. Magnetic field is an invisible field that exerts magnetic force on substances which are sensitive to magnetism. The direction of magnetic field is always from North Pole to South Pole. The path of the magnetic field could be visualized as shown in figure. Let us determine the unit of magnetic field. We know the force on any charge, that is electron or proton, can be calculated as F is equal to multiplication of magnitude of charge Q into the cross product of velocity of charge and magnetic field. Here, one important thing to note is, the direction of velocity and magnetic field is perpendicular to each other. If they are parallel, the magnetic field has no impact on charge. So magnetic field is equal to force divided by product of charge and velocity of charge. So force is measured in Newton. Charge is coulomb. And velocity is meter per second, so unit of magnetic field is Newton second per coulomb meter. That is named as Tesla. Suppose there is wire and the wire is carrying the current I. This wire will generate the magnetic field around it. And the shape of this magnetic field will be concentric circle around the wire. The direction of this magnetic field can be found by using the right-hand thumb rule. If you hold the wire with your right hand having fingers around the wire with thumb pointing towards the direction of current, then curl fingers would give the direction of magnetic field. The same can be observed in the figure. If you imagine the magnetic field is spreading out around the current carrying wire, the closer we get to the wire, stronger is the magnetic field. And further we go out from the wire, the weaker is the magnetic field. So the zone can be observed in the figure as stronger zone and weaker zone. Let us find out the magnitude of the magnetic field. Magnetic field B is equal to mu multiplying by current I divided by 2 pi r, whereas I is current carrying in the wire. R is radius at point which we want to measure the magnitude of the magnetic field. Mu is permeability of the wire. Permeability depends on whether wire is in air, water, vacuum, etc. Here, we can see the magnetic field is stronger when radius is small and magnetic field is weaker when radius is larger. Let's understand the magnetic flux. Before going through magnetic flux, let us understand what is flux in general. Flux is nothing but how much something flowing through surface in a given amount of time. So if you imagine in your house there is window and air is flowing at some velocity through the window, and if you keep rectangular pipe in the flow of air as shown in figure, the amount of air traveling through that hollow pipe in certain amount of time could be called as flux. What if we keep the pipe in this way, then how much air can travel through this pipe? The amount of air traveling through that hollow pipe shall be almost nothing. Air shall travel along the surface and not through the pipe. So how much of air flowing or flux depends on velocity of air and direction of velocity, direction of surface. Here, instead of air, we are going to think about magnetic field. Magnetic flux is defined as the number of magnetic field lines passing through a given surface. It provides the measurement of the total magnetic field that passing through a given surface area. Let us say there is area A which is perpendicular to magnetic field, so magnetic flux is nothing but magnetic field passing through the area A. Let's understand the Faraday's experiment. In this experiment, Faraday takes a magnet and a coil. A galvanometer is connected across the coil. A galvanometer is an instrument that can detect and measure small amounts of current in an electrical circuit. At starting, the magnet is at rest, so there is no deflection in the galvanometer. The needle of the galvanometer is at the center or zero position. When the magnet is moved towards the coil, the needle of the galvanometer deflects in one direction. When the magnet is held stationary at that position, the needle of galvanometer returns to a zero position. Now when the magnet moves away from the coil, there is some deflection in the needle but opposite direction, and again when the magnet becomes stationary, at that point respect to the coil, the needle of the galvanometer returns to the zero position. Similarly, if the magnet is held stationary and the coil moves away, and towards the magnet, the galvanometer similarly shows deflection. From this experiment, Faraday concluded that whenever there is a relative motion between a conductor and a magnetic field, the flux linkage with the coil changes, and this change in flux induces a voltage across a coil. Let us understand how current is induced in the wire when it is moved in the magnetic field. Let's imagine there is magnetic field and the wire. Now if wire is placed in the magnetic field and it is stationary, let us say there is charge Q sitting on the wire. Let us know voltage in the wire. There is stationary charge in the magnetic field. There is nothing going to happen as we have learned from the Faraday's experiment. So, force is multiplication of charge Q into product of velocity and magnetic field. So here velocity of charge is 0. So the force due to magnetic field is 0. Now if we move this wire to the left with the velocity v, as the wire moves to left with velocity v, the charge Q which is sitting on the wire will also move with velocity v. As there is velocity of charge is not 0. As per formula, we can conclude that there shall be some force due to magnetic field. Let's find out the direction of the force. It can be found by right-hand rule. So if index finger is the direction of velocity and middle finger is direction of magnetic field, then the thumb shall be showing the direction of force on the charged particle. So there is going to be net force on the charge in the direction of thumb. So the charge will move upward. Now imagine there are multiple charge on the wire, and all will start moving upward. What is called when charge are moving on the conductor? It is nothing but the current. So when we move the wire in magnetic field, current shall be induced in the wire. This is the basic principle on which electricity is generated. Subscribe Extra Class Academy for more educational content.